I was asked to share a few things, and Mark said it's going to be a great conference, and we'd like you to speak at lunch and maybe shake things up a little bit. So I don't know if that means that I'm not the great thing or whatever, but he asked me to step in. So I'm going to talk about a little bit of technology, and it's shifting gears a little bit from the in silico side of things to analytic chemistry, some natural sciences, but also some technology that we think is kind of helping us understand what's going on around us and protect human health. So basically what we're doing is using technology to turn Mother Nature into our witness and our engineer. When I look at this, it's a little bit bright in here. But what do you guys see? Trees. Trees. Exactly. Well, what are they telling us? What are they good for? Great apples. Let's zoom in a little bit. There's a little bit closer. I'm zooming in on one tree in particular. Anything change much? Zooming in, zooming in. Does anybody know where this is, by the way? Truman Park, exactly. So just down the hill from us here, zooming in a little closer on that tree. Bulb cypress that's been there for a while. And zooming in, and you can kind of see there's a little hole right here. And that's where we're going to focus today. We're going to try to understand what this little hole into a tree can tell us about the surroundings, and how Mother Nature then, through technology, can tell us a lot more. And basically what we took out of that tree right there was a little piece of the tree. And you see a few of you have them on your table right now. And think about what that tree is doing for you right now in front of you. Given the lack of time and lack of response usually, it's making oxygen, that's a plus, and it's using the water that it's soaking in. Great. But when we understand how that water is related to the water in the tree, we can actually use it as a proxy report. And when I go back to this site, nobody said this could be a potential Superfund site with contaminants in the groundwater that are cancer causing. By the way, it is. We'll get into that a little bit later. But we're using this then to see underground. And we're using a bunch of different approaches. I want to kind of get into technology. The simplest way we do it is to take an incremental borer right here. Forestry uses these all the time to look at wood and how good the wood is before they buy a forest. Okay? See the health of trees. So that's how we get these little vials and the samples in it. So you can see the annual rings in there. And with that, we carry a little bit of the groundwater with us. It's been filtered, it's been changed. We need to know the science to say how that mimics back to it. But all we do is place it in a vial, wait, test it with gas chromatography. So here's our high-end technology here that turns a little bit of a gas sample into an electronic signal that tells us compound X is there at concentration Y. But getting it introduced to this is kind of the trick, and then interpreting that data is the other trick within this. Then we look at this and we try to map the trees to the groundwater. So real quickly, here's Sedalia, Missouri. It's a railroad switching yard. And here's their site conceptual modeling. You kind of see concentric rings here that say, oh, there's a pollution right here, and that's a monitoring well they put in. Each monitoring well to get groundwater data costs anywhere from $10,000 to $40,000. And then it's going to be about $150 to $500 per sampling event just to get a groundwater bed out of it and look at that data. We went in and took 114 vials like this in one day with 4 people all over the site. And actually, the site goes way back over here. We tested everything. And we came back with a new model. We said, no, the contamination isn't there. There is some there. But the sources are here and here. So they've been trying to clean up something that really didn't exist. Let me show you what we looked at when we got underground then. This is actually, it's not soil. There was a hazardous waste repository there that was not reported for use. So we went through this. And if you want to apply this to a log canal, pond beach, places like that, it's the same idea. We don't know what's underground until we know what's underground. But using the plant sampling, this is the technique. Then we kind of had the idea, let's not take all these back to lab. We can do it pretty quick. We can turn around a couple hundred of these every 2 days. But we said, let's actually take some of the lab in the field to get more real-time analysis. I was actually on a sabbatical at another place, and I learned about solid-phase microextraction fibers. So this little guy right here, it's only 100 micron in diameter when I stick it out, is ultra attractive for organic molecules. So if I wave it by this, I can tell what perfume you're wearing today. If I breathe on it, it could actually tell me probably my blood alcohol content at some levels. They're actually using these in vivo in people to actually test chemistry. We can test for performance-enhancing drugs. Right now I'm on caffeine, ginkgo, and a couple other things that are academic performance enhancers. We can do that. We said let's stick that in the tree. So you see the little tree in front of you. As we've been sitting here, some of the molecules from that, and these are actually in an experiment, some of the molecules from the flask have moved up into it. Now we could pick them up. So we went forward and we tested this idea. So I said, let's put that in there. And in-plant sampling was born. And we used a solid phase microextraction fiber, and sake of time, I won't go through anything. So we developed a number of different sampling devices we could put into a tree, leave them there for sometimes a few seconds, sometimes days and weeks or hours, and get a signature then back on that. And we've actually hooked the gas chromatography directly to the tree also, and now we have the patent. We have the patent worldwide on in-plant sampling for groundwater analysis. And here's just kind of what it looks like. These are a little bit small. And if you want to get high-tech, this was the first time we ever used it. So we obviously didn't have these nice little corks designed yet then. That is actually a Pasteur pipette broken off with tinfoil shoved in it to seal it. So, high technology here to patent for S&T. In a matter of about 4 years from concept to let's file a patent. We're understanding more and more of this all the time. It really gets to the level of taking that data that we can get out of the tree and trying to assess it on a better scale. What are we really looking for? And what we want to understand more than anything is how does the concentration in this tree relate to what's out there, and then how does what's out there relate to what we're going to get exposed to? So we haven't even started the project yet, but the National Science Foundation is funding us to better understand how this tree and the concentration you can get right there relates to what we're breathing in residence. And well, why would we do that? Why don't we just sample as residents? Because if I brought dry cleaning in the day before, I'm going to have all kinds of dry cleaning compounds. If I had the windows open yesterday, the concentration is going to be lower. It varies so much. And then just to go there, you have to go knock on the door and say, I want to enter your home and test for hazardous compounds. That goes over really well. No alarmist action there. So we said, why can't we survey that? Because if you look at this picture, that basement is in the exact same environmental volume as the tree. And the tree is active. Let's go back to that for a second. Tree plants overall are about 99% of the terrestrial biomass on Earth. Okay? They're dominant. They move more water than all the rivers in North America combined. They're active. What are they powered by? Wind, relative humidity, sunlight. Does anybody know some place where people live and there's no trees at all? Okay, downtown New York City. But most of all, we like the plants. We actually surround them. We place them specifically around our homes, and they're sampling that same environment that we're breathing in. I'm focusing just on the subsurface stuff today, but we also look at the area part and what absorbs the branches that we're also breathing. So we looked at this, and this is in Cambridge, Ontario, just outside of Toronto. And just behind here, there's actually an industrial complex. You can see the bigger plots of land there. And we went in, and we sampled people's trees, and in 2 days, we mapped out this plume. And the spots you see there are color-coded for hot concentrations, low. And if I draw a circle around all of our hits, you can see then we've color-coded the home concentrations too. And we can say, well, we hit about 95% of the concentrations in there. And these guys, yeah, there's some in their homes, but they're separated away from it. It turns out that the compounds there were brought in from dry cleaning, the same compounds. So we did a better job, essentially, assessing this in 2 days than they've done in 2.5 years at a cost of about $1 million. So that's what we're trying to get to. And then we didn't alarm anybody other than, what are you doing to our food? No, we're taking this little tiny sample and we're going to get off the land in just a second. So it's a very quick screening tool. It's not an absolute. It doesn't tell us what the concentration is. But if we go back to this, and if we understand through partitioning technology approaches what this plant tells us versus what our homes are exposed to, and if you have a sealed basement, you're bad problem. If you've got a well-ventilated basement, it's going to get out there too. But it tells us that potential. And then, actually, while we're there, this is in Cambridge, and there's some of the homes we were sampling also. We had the idea to hook directly a gas mass spectrometer right to the tree itself. So in a matter of about 10 minutes, you can barely see it with the lighting here, but trichloroethylene is not only there, but we know what the compound is and the relative quantification of it. bad thing is this technology costs about $150 a pop versus the little samplers you saw are about 20 cents maybe. Don't tell anybody. We charge a bit more than that. And as we're putting this out there, a forensic scientist from France actually called up and said, hey, we're doing a project, would you like to jump in with us? And they've been working with a lab in Sweden that looks at X-ray diffraction of tree rings and then goes back in time and says what was the past exposure. So they can look at inorganics and actually post-date them when the exposure was. And then we're doing the real-time organic molecules. So our two labs are kind of the central theme of this 26 investigators. And last year we won the top technology prize, and Nicole is essentially the industrial groundwater and soil protection agency of all of Europe. So through that, we're doing a lot to try and then compare our data. You can see the data down here, we don't have time to it. But each one of these samples gives us about 40,000 data points that we've got to then manipulate and look for subtle changes in those concentrations, because each annual ring doesn't sample just that year. It's actually sampling some composite of that year and somewhere around 5 to 15 years into the future as well. Because if they act over time, they shut off, it's not going to flow. But then some molecules actually drift in and out. So there's a lot to understand here. So this anomaly, we can actually track back through the technology, through the statistical comparison of different ions and also. And we can go back and say around 1990, there was an increased exposure at that spot. It's really valuable to try and trace back to who was responsible and understanding it. And here's just a look at that. So all the data points down here, and kind of how it works. An X-ray beam is bounced off of it, and different atoms give a different X-ray diffraction pattern of that. I don't understand. It's a number that comes out of the back of the machine without reading it. And then we had another area. So everything we looked at previously essentially exists as a gas. It volatilizes off, and we use that as our cleanup step. But a lot of problems we have are not volatile. So we started looking at explosives, and the Department of Defense offered us to do it. And in about 6 months, we came up with a way to go from fresh plants, we flash freeze them, and then we put them in a vial like this with a molecular sieve in there that only lets small molecules through, and mostly explosives are pretty small molecules. Spin it around at 23,000 G for like 20 minutes, and we can go from fresh plant tissue all the way down to, and this is going through a liquid chromatography, a triple quadruple mass spectrometer. Again, a fancy machine where you put a sample in this end and the number pops out that end. And within that time, we got this relationship from what our exposure concentration was, what you're seeing there, to our analysis. And this is kind of the amazing part. We cover 6 orders of magnitude. So we can go from part per trillion to part per thousand and screen a sample in under 2 hours. And again, don't tell them, I added a cost of about $30. Okay, we're charging a bit more. A traditional analysis takes about 115 hours, and you get it back in about a week. We're doing it in about 2 hours. So kind of to wrap it all up, when you understand those things, we can start to look at all of these processes in science that we really could not understand before because we didn't have the technology to see it. We're looking at parts per trillion, parts per billion of contaminant molecules, organic, in an organic matrix. So it's looking like looking for a needle in a stack of needles. And you got to find that one, and it's 1 in a billion. So through technology we've developed here, we're able to understand all this now, and actually now we're back to projecting and saying, now we can better understand how Mother Nature works at this root-water interface, and we're actually putting out a science paper that we can better predict what molecules will move through a biologic membrane. And we're actually starting to understand that membrane is a lot like our blood-brain barrier and our intestinal membranes. They're very similar. They're different. But we can screen molecules, new compounds as they're invented. We can screen them and say, do they enter a plant or do they not enter a plant in a matter of hours versus you can imagine what mammalian studies costed to do if you have dose medicine or anything else. So go back to Schumann Park and wrap this up. There's Schumann Park. Here's that tree I was looking at in the picture. No, this one right here. The tree we're looking at in the picture. So unfortunately, here's our greenhouse where we've done a lot of the studies to understand the science before we project out. That's Schumann Park. Here's Bisbee dry cleaners. Remember we mentioned dry cleaners? Well, it's not really dry, it's just not water. So they use organic solvent to clean your clothes, and every back door of every dry cleaner in the country pretty much has some standard practice. The law is broken, 1950s, 1960s, solvents get dirty, out the back door, keeps the weeds in. So there's their suspected plume, and here's the concentration zone. So we actually did this as part of a class. We went out and sampled the entire park within a 50-minute class period and had samples back on the GC by the end of class. Now, you see these both these pictures. Anybody notice the difference? Other than better resolution. Buildings there, buildings there. Okay, they put in a parking lot here. Right here, we didn't have any data. So we planted 210 trees to go right through where the plume was with the city. Now this is real alarmist. You know, planting trees in a park is kind of crazy. So we essentially did that 210 solar-driven sampling points, and within, somewhere else I had a picture here, but these are over 35 feet tall now. So the trees you see in front of you, given proper light, fertilizer, they're massive growers. So we can actually pick the right species that we know uptakes the compound. We can put them where we want it, even if we don't have a tree. And it's far cheaper and relatively faster than we can set up a lot of sampling. By the time you get permits, get easements, get on somebody's land, it's a lot easier to walk in down and plant trees. And since we're technical people here, it's okay, we can admit it. I wanted to get into a new approach we're having, working with both engineering, and we're trying to come up with a technology where we can do this real time. So we're working on new sampling methods where we'd actually be able to get the data in 30 minutes or so, and then enter it real time and map it up, plot it out, and if we start sampling and the concentrations are going down, we turn around and we go sample this way. So within a day's time, we not only get sampling, we get directive sampling, we like to call it organic. Where the public will say, oh, it's actually growing as we do the data. So directly put it in there, get it out, map it up, right back to us. And this is actually a site where we're doing it. This is set up handfill. So we're plotting each and every tree. We got the size, we got the growth, we can look at concentrations over time, and then we can get to using that as a monitoring tool. Overall now, it's the same picture I showed on the first slide. I see it a little differently. I see an active sampling, solar-driven device that's got about 4 billion years in development. It's excellent mass transfer. That's what it's designed for. Again, the biggest biomass on Earth by far, and it never moves. Okay? Everything it built is built from sitting there. So it's constantly probing out and actively sucking that environment while it's getting our molecules through. And we just had to figure out how to listen to Mother Nature and get it back. So with that, I want to put in here, so starting in Rolla, that's how many active sampling sites we have. There's my timer, good spot. So we've done over 50 sites in 14 states and 8 different countries, and we're still active. We actually just got samples from Switzerland on Thursday, and we sent the data back today. So in under a week, pretty much anywhere on Earth with FedEx, we can have somebody sample, get it back here, and pop a map out and deliver it to them anywhere now with our network. And just to wrap up, this is also in Schumann. This was our first sampling. So this was my class. So these students had about 15 minutes of prep time. And there's the traditional sampling methods and the waste that they generate. And they can do about 2 sampling wells a day with that technology. We can do 115. We know that with a team of 2 people. So, and that's all of our equipment. We go to the field with us. We can bring everything along with us. I used to bring it and carry on. We don't have to do that anymore. But we can go through check luggage and carry everything we need to the site and come back very briefly. So, what's next? Climate change. And actually, we put together the state of Missouri, we called it Transcept. And the idea was that we'll use plants to monitor this. So this is actually the plant stress as indicated from satellites during a drought. If we start to better understand and look at all the spectral images, not just the visible spectral, but the hyperspectral, we'll be able to see plant changes over time. Is our expectation. And a lot of our economy in Missouri is based on plant systems, either agriculture or forestry. And we'll write that. Last year, not year to last year, USDA moved our climate zone 200 miles north. our basis on plant systems, how many new invasive species are we going to see? How many different changes in our plant systems over time are we going to see? And can we be reactive or proactive in trying to do that? So, with that, I thank you. Enjoy your time here at S&T. If you're from abroad, travel safely. Abroad being like outside. And I'd love to answer questions, but they might be hard, so I'm going to leave. So we're at the point once while I'm packing up. I need my plants back. By the way, there's no chemicals on your table. These are going to be dosed with dioxin, not dioxane, and perchlorate next week. Thank you, Megan. Question? Yes?
How much physical force is required to take one of these samples?
It depends on the tree. A lot. So I've got a big bar to try and get into. Black locust is horrible. Some of the harder woods, it's really hard to get into. But like the willow or poplar, I mean, I can spin it with one finger once I get in. Oh, and our new technology, Brewer Science asked us to evaluate. They're coming up with a sampler. It's essentially chemistry on a chip. So we're looking at, can we put that into trees and get real-time data reported to us with remote sampling. So once we understand the molecules are there, pretty much any technology that pops up on the market for assessing molecules in the environment, we're going to be trying hot to get them on board and see if it works in a tree also. Anything else? Now I have to go teach public health. So enjoy your lunch and your time.